In this problem, we want to show if a and n are positive integers, where n is greater than 1. If this is a prime, a to the n minus 1 is a prime, then a has to be 2 and n has to be prime. And this format, whenever this form of an integer is a prime, we call that number as Mersenne primes. Now that's why people try to look for primes in this format, like 2 to the prime minus 1. So whenever that's a prime, then a has to be 2, n is prime. That's what we are trying to prove. Now to prove this, we're gonna use proof by contradiction. Suppose n is not a prime, we are gonna assume that the conclusion is not true. So n is not a prime, that already says the conclusion is not true, right? So we are gonna say if n is not a prime, which means a composite number. So if n is composite, then n is equal to a product of two integers, say k and l, where these both integers, they must be in between 1 and n. Specifically, k has to be in between 1 and n. Now, here's the trick. A to the n, right? Because n is kl, so a to the kl, this is a to the n minus 1, which is a to the kl minus 1. And this guy actually can be factor. It is quite, this is a pretty useful identity. It can be factored as this: a to the k minus 1 times a to the k times l minus 1 plus a to the k times l minus 2 plus a to the k times l minus 3, and so on and so forth, plus a to the k plus 1. Okay, so here the powers are multiple of k, multiple of k's. Well, you can actually check. Let's just quickly check so that you are convinced this is true. Let's expand this. So we are going to multiply these together. You have a to the k times a to the k to a to the k times l minus 1, right? And then let's take a look at what this is. This is a to the k times a to the k l minus k, and then which is a to the k plus a kl minus k, and this can be cancelled, right? You're left with a to the kl. So the first term, you're left with a to the kl. Now the second term, take a look at this guy. You have a plus a to the kl. If you do the algebra again, this is, you have minus 2k. There's a power k, so you end up with like just 1k, right? So you end up with just minus k, negative k. And then the next one is here, will be a to the kl minus 2k, and so on and so forth. The very last one will be a to the 2k plus a to the k. So that's what we have. And then let's erase those. Oops. Okay, don't know why it cannot be erased. Oh, I can erase that. Now let's continue to expand. This time we need to multiply this, right? So the first one is negative a times k to the l minus 1, and actually, which is the same as this, they can cancel, right? The next term is this guy, minus a to the k l minus 2. These two can be cancelled, and if you do that, they actually can be cancelled a lot. So that very second to the last one is minus a to the k The very last one is minus 1, right? So all these can be cancelled. Actually, you're left with this term and this term. And let's take a look at this term. This term is equal to a to the k plus kl minus k, if you like kl minus k here, which is a to the kl. That's why this can be factored as that. Well, you might wonder, hey, sometimes you don't know how you can come up with this idea. Really, it's just the more you see, the more you know. In the future, you will know how to factor this one. This is a pretty smart one. I don't think I would be able to come up with this one if I don't know that ahead of time. So that's the first step. This can be factored as this product. And let's continue. I'm going to erase those. Now, therefore, you can see that a to the k minus 1 divides this piece, which is a to the m minus 1, right? And of course, because it divides that, and a to the k minus 1 will be less than a to the m minus 1. We do know that this is a prime. We do know that this is a prime because a to the m minus 1 is a prime. Therefore, a to the k minus 1, the only numbers that can divide prime is either a self or 1. Now, this is not a self because it's less than a to the m minus 1. It has to be 1 in this case, which means a to the k is equal to 2. Now, take a look at here. In order for you to get they're both integers, right? In order for that to be 2, the only way that can happen is a has to be 2 and k has to be 1, right? Now, I hope that you see a contradiction right here. We are going to say when we assume n is composite, when we assume the conclusion is not true, we know n is equal to kl, k is in between 1 and n. Now you see that k will, after, when that's true, k will lead to a k equals 1 conclusion, which is contradiction right there. K cannot be 1. So, therefore, a contradiction. What we assume is incorrect, right? Therefore, n has to be prime. N has to be prime. And furthermore, a has to be 2. So that completes this proof.